Grant as project manager for NASA Ames Sustainability Base. I work for AECOM, and we teamed up with McDonough, Douglas, and a few other consultants for this project. And I don't want to leave other consultants off the list, although they're not here. One of which was Loises and Opelode, a really small firm in Alameda, who are, I think, is a backbone to the success of this building. And they're unspoken heroes, and I just want to give them some acknowledgement. NASA is a client of AECOM's for about 20 years, particularly this campus, NASA Ames in Mountain View. And it's about 127 buildings, 3 million interior square feet of office space, of which 44% are beyond their useful life. We started the master plan for them and completed that master plan in 2006, 2007, in which we recommended a renovation by replacement program. NASA Ames Sustainability Base is the first of 5 new buildings, and in order to accomplish this one building, the agreement is they must demolish at least 1 equal square foot per new structure. So for every new square foot of building, they're going to be demolishing a single square foot or more. This building is 50,000 square feet. It will house approximately 200 to 220 employees. It is also a research facility as well as administrative and conferencing. I'm going to hand it over to David, and this is just a little timeline of the experience we had with NASA starting out actually in '98, when they had this vision of reaching out to the broader public and the university, going from a closed campus military site to one that embraces the wider research community in Silicon Valley.
Hi, everybody. This session is so important, and I'm so happy to see everybody here. It's amazing what Autodesk is doing. We started this project in May of 2008. It'll be completed in May of this year, which is pretty fast for a federal office building. The ambition here was, what if we could imagine NASA's first space station on Earth? As the engineers could be inspired and be developing the control technologies that would go to the moon and then to Mars. So that's what this assignment was. The site is a foreground site that we actually helped them choose. So it's shown there in red. Part of our ambition was to reflect the culture and the context, and to be native to NASA's campus here. So what we did is we looked at these giant buildings. You'll recognize this one. And these buildings that had exoskeletons that allowed for free, undisturbed space on the inside. So our assignment was to study this site, and as we do it, we use BIM tools to understand the sun and the wind, and to have a deep understanding of the passive opportunities for this building. It's a key to the success of this building, as it was going to be a model for federal standards to gain as much efficiency and to be effective. And so what we did is we know this climate pretty well. We've done a number of buildings in the area, and we know where the sun is and where the winds flow. So we actually created a footprint that would be optimized for the sun and the wind. It's a narrow plate. It's 50 feet, column free, has incredible daylight penetration and passive ventilation through each floor. It's designed in a cluster, and you notice that some less frequently occupied spaces like conference rooms are on the north side where they'll have less sun. An important aspect to this project, as June will expand on, was using the model to communicate amongst a team of engineers and several offices around the U.S. And so as we were freezing certain elements like the structure, here the frame showing the exoskeleton, that work would be started, and we would continue to work and to develop the model and to focus on the skin and the exterior envelope. This isn't my slide. I wouldn't put together a slide with with this density of text. This is NASA slide. What this is showing in bold is all of the strategies that they are incorporating at this time. And then the unbolded are ones that the building anticipates are going to be studied in the future. You'll see that the human factors and the controls are key to this. This is really a ground truthing station for developing controls that will react live to the environment and the systems that they are going to be engineering on. We use all of the tools within the suite, but we also use the model to communicate with our colleagues here at Aloysius and Bellote. They use additional tools, the tools that they have modified in-house. This is a version of radiosity that's showing daylight penetration into the space. But the model was the tool that we used. And then they also generate views like this through tools that they've customized that take a look at glare reduction and sun shading. I'm going to show you, as a result of the modeling, some of the performance projections that we showed here. So on the left is a base case, a standard high-achieving, compliant building. And just through our focus on passive strategies, the first step was just the efficiency gains. Then the building is optimized for PVs on the roof and on a parking structure. It shows where we would be if we were to have PVs, and then by putting some additional PVs on the parking, it was anticipated that the building would actually produce 22% more energy than it's going to consume in modeling. As it turns out, they have decided to put in a next generation boom box fuel cell. And so with that technology, they will actually be producing 20% more energy than the building will use. Water and waste, these are the people that send water to space that needs to be consumed several times. And so they understand water quite well. So we actually worked with them to develop some of the strategies. And the overall water demand we project to be 13% of a baseline building. And as is, we'll have very little effluent that's going to leave the site. And there will be a black water treatment plant in the future that we've identified on the site. And so there will essentially be no effluent from the site. So we'll be producing more energy than we consume, and no wastewater. And we need some water for drinking, so we're going to consume about 13% of the water we normally do. And but most of all, I think NASA is going to have a building that's going to start its life upon the construction completion. It's going to be used to develop testing technologies that are going to carry on for 50 or 100 years in the building. So we aren't done. We're just starting by completing this building. June?
After seeing Autodesk's presentation about the software tools which are now available, which weren't available to us 2 years ago, being a little bit archaic. And David just mentioned NASA is creating some tools, and this building will be forward-thinking for about 50 years. I have a feeling that some of these tools and monitoring systems will be obsolete also in 2 years. So for me, this is really exciting. And I'm going to approach the building and discussion from a technical perspective, but not get too engineering because I focus, because I have a feeling the audience is mixed. And also, just to give you some background information about the history of how we got to this form. So here are the goals we started with. We want a healthy environment for 200 employees. We want a high-quality space with great air, great light. We want extreme natural light. We want to utilize low energy to as much as possible. We want to provide intelligent controls, because this is NASA after all, and it should operate like a space station. We want the building systems to be flexible. NASA has a history of relocating offices on a consistent basis. So hard walls and fixed walls were not something we could actually recommend, and not suitable for this environment. We wanted no air conditioning if possible, which is revolutionary for us. But we thought, given where we're located, this might be doable. And it had to be, actually, it should say platinum and beyond. We didn't know what that meant, but we were going to shoot for it. So here's the final floor plan, and David showed a similar one, but this demonstrates some of the airflows that were intended and should be experienced as a result of the final design. And you can see it's a very thin building with intended natural ventilation. The wind patterns definitely from the north. There should be a cool space to work in and very light-filled. This is a section through the structure of the building. It shows you all the bells and whistles. As it's attached, we have, this is the structure, which is actually not just a vine screen, which would provide vertical shading, but is also our seismic system. So this is revolutionary for us because typically, if you know anything about, you've seen all these buildings with the X's in the windows as they brace the building or upgrade the building for seismic performance. We did not wish that. We wanted a clean facade, allowing us to open the windows as much as possible, vertical shadows, but also we required some shading because you're going to get extreme glare and, at certain times of the day, certain times of the year. At some times of the year, vertical shadings is most appropriate, while at other times horizontal at 2 levels is also important. So here you have the kit of parts. We have the window system as it's intended to operate. We have our underfloor air system. We have our vine screens. We have our exoskeleton. All of these systems have to come together for this thing to work. We decided also that if we're going to go platinum and beyond, why shouldn't structure be considered too? And our structural engineers said, well, you know, since the engineers are getting a little bit of recognition for their knowledge, why can't the structural engineers be included in part of this adventure too? So we spent some time really trying to figure out what is the optimal size of this building. We went from 65 deep to 50 deep to 55 deep, and the constant negotiation between the height and narrowness of the building in collaboration with the size of windows had to work. The structure was not an isolated feature. It had to work in terms of, well, if the bays are too wide, if they're wider than 35 feet, what size windows are we going to have? How much is that going to add to the cost of the building? How is that going to improve efficiency? So there's a constant dialogue between structure, between mechanical engineering, and between architecture. What does it look like at the end of the day? Here's the final structure as it is in our Revit model. And our engineers, in fact the entire AECOM team, were working real time on the same server. The model was housed in Orange. My team was split between 5 cities. I'm in San Francisco, one other architect. The mechanical engineers and structural engineers in Orange County, our fire protection guy in Albuquerque, some of the consultants here in Alameda, and so it became our system to work, which was the Autodesk Revit model. And honestly, I couldn't have done this project without it because we were given 9 months to do a project which would take typically 18 months. And here is the final building under construction as of a few weeks ago. Now we're going to go on the inside. This is an image of what the ceiling looks like. NASA decided, why hide the mechanical systems such as this space? And if you look at this space, I believe these are acoustical ceiling tiles, which is great. We were looking at how do we use the ceiling as an energy source. And one of the things we decided that NASA wanted an industrial look, which worked with this site, because the site is very industrial in feeling. It is not a pretty campus. We also had to decide what was the best mechanical system that would work with this environment. So we went through a few scenarios, one of which was the radiant concrete slabs, which are extremely efficient. It's just concrete with water flowing through it. However, radiant concrete slabs are slow to respond. And this site, Mountain View, can start at 60 degrees in the morning, go to 100 by 12 o'clock, and drop back down to 60. Radiant concrete slabs can't handle that. So we modeled that experience, realized it was a no-go. We also looked at the other extreme. What if we did complete natural ventilation, just the air circulated through the space, through wind, and realized that 16 days of the year, this would not work. The interior space would would rise 85 degrees. And again, this is not a very comfortable environment. We spoke to NASA. They were always part of this design process. And they decided, well, 16 days of the year, people can work outside, they can go home. And we said, you know, I could see a few lawsuits coming downstream, so how about we have a backup plan? So we also looked at on-the-floor air systems, which are dependable, but it's passé. NASA wanted something revolutionary. There were on-the-floor air systems practically in every new building now. So it was eliminated because it wasn't new enough. So we also looked at chill beams, which are great efficient systems, and it results in like a spine rating system in your ceiling, but they're not very flexible. You end up having to place your walls where the ribs are. So that was eliminated. So we ended up with this hybrid system of radiant ceiling panels in the office spaces, and the cooling panels drop cold air from the ceiling. We have heating panels on the sidewalls, and we also have a raised floor. And the reason why we went with the raised floor was to manage the cabling systems, because we needed the walls to be as thin as possible to provide flexibility. But a raised floor, even though we had no intention of using it for air distribution, was a convenient way to manage cables. That became our backup system for those 16 days. We would use that on the floor to push the air during those 16 days, should there anyone be in the space that chose not to go home and work. I would have chosen anyway. We also had abnormal spaces, and the abnormal spaces was a connector bridge between the two buildings, the lobby. And because that space is not occupied 100% of the time, it could be a slow response place. So in that location, we chose to use a radiant concrete and natural ventilation throughout. So there are no cooling panels in the ceiling in this space because it's not a inhabited space. It's a pass-through zone. So you kind of provide flexible and less expensive technology and let nature cool the space or heat it depending on the time of the year. So the building is not a one single item that was specified and replicated throughout. You have to design it for the particular experience and environment as it dictates. And here we are, just a model of the office spaces. And I want to point out workstations. We saw an image from Voices of Glory. Workstations is, for me, the success of this building. NASA has a history of 5-foot-high cubicles. At 5 feet, you can't get daylight to penetrate deeply into the space. They had tried implementing low cubicles a few years ago, and there was literally a revolt, and the trade unions decided they were going to not have this. So there's a 3-month of training and negotiating, but we needed those workstations to develop. Here's an analysis of the on-the-floor system during those 16 days when we do need it. And here it is again. And here is the control systems. And because it's executive parts, something has to manage it and tell the windows when to open and when to close, when the cooling system comes on, when it does not. So we have 5 strategies built in the computer, which are here for when interior outside temperatures are low versus when interior outside temperatures is a wider variation, and what to do, when is heating required, when is cooling required. The backbone of all this is a geothermal well, which exists on site, not directly under the building as we originally wanted it, but in an empty field across the way. We originally started with 72 wells, and we hit an artesian layer at 300 feet, and we had to have 100 wells, which are only 150 feet deep, and here is when we hit the artesian layer. And this is quickly a demonstration of the water strategy. We're not talking about water, I think we're just focused on energy. But as David said, and here is our irrigation tank, which will do part of the gray water treatment, and it's buried on site, and it irrigates the entire site as well as provide gray water back into the building. Here is the Revit model as used by the construction engineers and the general contractors, where all the systems in the building has been modeled and tested for clash detection and then used through the construction process. So we took David's McDonough's model, we elaborated on it, fine-tuned it, analyzed it, came back with suggestions, and then the model was handed over to the construction engineers. And then NASA has their own spin, where the put various monitors on the building, and they're constantly fine-tuning how they're going to gather data and use this building as a research tool rather than just a standalone building. So it's in constant transformation, even though they have not moved in as yet. And here's just a quick list of the green features that are in the building. And here is our performance as we estimate that we're at target for. 78% reduction in energy, almost 90% reduction in potable water, and 25% energy production from photovoltaic panels. But the great thing is what NASA is doing now, and they're looking at installing wind turbines, which David said, in addition to the fuel cell, they should be almost able to sell that energy. So just from this facility and a few campus strategies. So in a nutshell, that is the NASA building, and we will be occupying it May 2011.